Okay, so last time we tried to get this to work, this surface has projected successfully on this projector once, and that was when Robert was the only person in the room. So don't get to see the live thing. After we're done, which we may be done a little bit early today, we'll see. You should come up though and take a look at it, because on the breadboard here, I've got a 1 and 2 pole RC filter, and we calculated the corner frequency of one of them last time. In fact, I think it was not this example. So what we said this does is generates a sine wave. We do a frequency sweep from 100 hertz to 20 kilohertz in relatively small steps and measure the gain, the output of the filter, and the phase lag of that sine wave. And so this is a single pole RC filter's output. So you can see we've got, in this case, the corner is way down here. It's, I think, 150 something hertz for this filter. And then we've got some roll off after that. So at 1,000 hertz, we're 30 decibels down. At 10 kilohertz, we're 60 decibels down. So this is actually a 2 pole, right? Because it's about 40 dB per decade. So it's not single pole. And then you can see the phase shift in degrees. That's minus 60 degrees, minus 150 degrees. So this is where running your signal through an RC filter has this frequency-dependent phase shift that can really mess you up if you don't know that it's there. Everybody good with that?
Is it a virtual oscilloscope?
Yeah, this is a LabVIEW program.
Is it available? Did you program it?
It's available. It's part of the, they have this suite called Elvis, which stands for something clever that I don't remember. And they have a bunch of different tools, oscilloscopes. This is called a Bode plot. When you're looking at the output of a filter like this, it's called a Bode plot. So this is the Bode analyzer. You can pick up one of these things. This is called MIDAC. National Instruments made them. I think they still make them. Electrical engineering students used to be required to buy them for their coursework. So you can pick them up on eBay for 150 bucks now, whereas new they were about 400. Kind of a nice thing to have, you know, in the desk drawer when you want to figure out something like this. Okay. All right, so today we're going to talk about PID loops and PID control. I'm going to show you some videos when we get there. Let me pull up a slideshow so we can blank out the projector, because again, we're going to be working on the board. And then we'll show some videos when we get to the PID part. How are people's projects coming, hopefully coming along, because we only got a couple weeks? Yeah, okay. Chris and I are going to put the presentation requirements up, hopefully, later today. Okay, so today, since we've already done filtering and a lot of the basics of signal conditioning, we're going to do control systems. So what is a control system? Does anybody have a definition that they think is what a control system means to you, philosophically, emotionally, religiously, whatever? No one has a comment on what a control system is? Okay, so it is a device or set of devices that manage, command, direct, or regulate the behavior of other devices or systems. So you can think of, in the lab, we have, you know, like a pressure regulator on a tank or on an air compressor that controls or regulates the pressure from the air system that we have. So that is a control system. They don't have to be electrical. We can have mechanical control systems as well. We're mostly going to focus on electrical. But, oh, and the process or system, a lot of times you'll hear that called the plant in engineering literature. They always talk about the plant. It doesn't have to be you're controlling some large thing. It can be a pretty simple process. So what are some examples of control systems? And we're not moving on until somebody says something of an example of a control system you can think of. There's lots of them around you. There are multiple in the room, I would say probably. A thermostat, yes. It's the most common. Anything else anybody can think of? A dimmer, yeah. A dimmer is a good one. Yeah. Yeah, remote control, sort of, I guess you could say. It's a command device, yeah. So one that people often forget about is cruise control in your car. That's actually a PID controller that we're going to talk about later. And I'm going to show you some examples of poorly tuned control systems. My car, which is a 2011 Ford Escape, has a PID cruise control that is poorly tuned. And I discovered this if I was going up a slight grade into the wind under very certain conditions, you actually could see the speed of the engine start oscillating, and it would end with the engine going rah, rah, and then the cruise control would kick off because it detected there was a problem. That's a poorly tuned control system, and it has some real implications. Some more things that you could have in the lab, hydraulic ram positioning, like we have on the Timcos and the Biacs and all kinds of stuff up there. Servos, which could be like the servos that are in your kit that some of you are using on your projects, or other servo control systems. And another everyday one, printers. Printers have all kinds of control systems and feedback in them to position the print head to detect when there's paper and keep trying to feed paper until they eventually jam and all that kind of good stuff. Okay, so there are two main classes, and I'm going to put that in quotes, of control systems. Any ideas? So, no, not quite. Similar idea, but we call them open loop and closed loop. So open loop and closed loop control. Okay, so we'll start with open loop, which is the simplest of the systems. So an open loop controller has no knowledge of the outside world, or state of the system. It executes predetermined outputs based on a basic model of the system. Okay, so the example that somebody had earlier of a dimmer being a control system in a room, that would be an open loop control system. Right? The dimmer has no knowledge of what the light level is in the room. It knows that I walk over to the switch and I turn this up or down, and the little fancy lights up there that don't really do much are changing, but they're going to some relative position on here. If there were more lights on the circuit or less lights on the circuit or more sunlight or less sunlight, it knows nothing about that. It just goes to some predetermined position. And that's fine when you have somebody standing there that's able to control it. And in the engineering world, they don't call that, the person that stands there and turns the knob. They call it feed-forward control when there's somebody that's standing there adjusting the system continuously in an open loop. Okay. So any other examples of open loop controllers that people can think of? Got a couple. One that everybody uses, which is a timed clothes dryer. And another would be like a CNC machine. So a timed clothes dryer, right? You put your clothes in, you crank the knob over to 50 minutes or 60 minutes or whatever you set it to, and you hit go. It runs for the duration of that timer and then stops. It knows nothing about if there are clothes in it, how much clothes are in it, how wet they are, nothing. A CNC machine, like those machines that we saw at the machine shop or 3D printers, they are really open loop. They get a home position, and then the stepper motor says, I need to go 3,000 steps over, 3,000 steps back, and it just counts steps to know where it is. There's no continuous position feedback on where that print head is. Okay.
There's also time to track lights falling in.
Oh yeah, yeah. So
sometimes work and sometimes don't. We have them on North Africa these days.
it's true, yeah. So they don't have any kind of sensors in the road like the one that you all programmed when you did a better job of managing a traffic light than a lot of civil engineers. Okay. So we're going to make a little diagram of the timed clothes dryer. So we've got the desired time, which is an input from the user. That goes into a timer, which in this case is the controller for the system. And there's also electrical energy going in. That's connected to some heating elements. Which are going to be the output of the controller, right? Whether the heating elements are on and off. The heating elements put out heat, which go to the clothes, which the engineers would call the process or the plant. And the output, what we perceive, is the actual dryness of the clothes. And it seems silly to write a diagram like this out for a pretty simple system, but when we get a little bit further, you'll see that these diagrams get a lot more complicated pretty quickly. Okay, so an open loop system will, we would say go to or drive to their set point no matter what is happening with the system, because they don't have that feedback, right? That can be a very bad thing when things go wrong. So there's no error correction capability. One of the YouTube channels that's linked in the resources section of the website is it's called NYC CNC. It's a guy that does a lot of CNC machining in Zanesville, Ohio. This week he just posted a video that's 6 minutes long of all the times that he has crashed the tool head of his CNC machine into what he's doing on accident. Because the CNC machine has no feedback, right? Has no way to know how much force it's exerting, has no way to know if the table's in the right position that it actually needs to be. So bad things can happen. You can get runaway loops with this. Some 3D printers, the way they control their temperature it wasn't strictly open loop, but they didn't do it very well, and they would just keep heating up and catch on fire. So that can be a bad thing. They also can't handle disturbances, which is related. So this would be like if instead of having a cruise control that was a closed loop system on your car, if you had the old style cruise control, which was a stick that you would wedge onto your accelerator pedal, let's say. Or I know Chris made one for his motorcycle that was like a clamp, right, for the throttle? Yeah. So if you just clamped the accelerator to a constant acceleration. That is fantastic if you're driving across Kansas and there's no wind, because it's flat and the conditions are the same. There's no curves. If you hit a hill, if there's wind, if you're taking curves, that's going to require more or less power from the engine. And if you're in an open loop system, it has no way to know that. And you're going to be going 80 or 90 down every hill and 20 up every hill, right? So it's not going to be a very good solution. All right, and then we said if the human sees some kind of problem, like if you were going up a hill and you adjusted the board on your rudimentary cruise control, that would be called feed-forward feedback.
And I guess these days the dryer has been upgraded with a humidity sensor, right? You can make it more dry or less dry.
Yeah, a lot of them have that kind of thing there. You just set how the dryness that you want instead of the time, which is really nice. It's probably also why they're, $1,000 for a dryer. Okay, so the other type that's a little bit more complicated, is closed loop control. Okay, closed loop systems have feedback. So when you see the word feedback, you should already be thinking operational amplifiers and all that negative and positive feedback. It's all going to keep coming back from the process. They are controlling and can therefore adapt and make corrections. Okay, so what are some examples of closed loop? We already had moisture sensing dryer. And cruise control on a modern car. What else is a closed loop system? Traffic light with sensors, yeah. Somebody else said one earlier that is as well. Thermostat.
In theory, unless it's the kind of thermostat we have in our offices here.
Yeah, those are definitely open loop.
I call those scientist switches.
Yeah.
Really do anything.
Yeah, just press the button, nothing really happens. So in your apartment where you have an actual thermostat, it senses the room temperature and then it turns the heat or the air on or off to do the right thing.
Something is just on a timer, is that technically closed loop control? Like I have a curling iron that shuts off after 60 minutes, but it doesn't know how hot it is.
That would be open loop,
Okay.
right? So it has no knowledge of the outside, the process of the curling iron being heated, right? Okay, so now we're going to make the diagram a little bit more complicated for our moisture sensing dryer. So now you put in desired dryness as the input. That goes into the controller, just like before, except now the controller's not a timer. And we have electrical energy coming in as well. That goes to the heating elements again. Which produce heat that we give to the process or the plant, your clothes. The output is the actual dryness, again. But what's different is here we put this path in to our sensor, and it produces a signal that we feed back to the controller. Does anybody know what the signal is called in a closed loop system? The difference between where you want to be and where you are. So we want to be at a dryness of 11 because it's a Samsung dryer that goes to 11 instead of 10, like the LG ones. And we're at a dryness of 6. So what's the difference in those called? Same as in an op-amp system. Because the feedback loop, it's the error signal. Okay, and this entire section here, so this part of the loop in green, is all called the feedback loop. And in this situation, it's pretty simple because we've got one sensor, one variable, one knob that we can turn to affect that variable, which is whether the heating elements are on or off. It does not have to be that way. You can have many variables and many things that you can change, and we're going to get there. Okay, so closed loop systems are robust to external disturbances. They have a reduced sensitivity to the exact system being controlled. And they're generally more stable than open loop. Generally, that's a dangerous thing. So the first one, robust to external disturbances. If you have a timed dryer and you open the door to check on something, the timer just keeps running, right? It's a mechanical thing in there. So you're losing that time. So it's not robust to disturb if you open the door for a very long time, let's say. The reduced sensitivity to the exact system being controlled would be like every dryer that's manufactured is going to have a slightly different heat output. Or every car, even if they're all the same model, if we said to go 70 miles an hour, you set the engine to 2,300 RPM in fifth gear, that probably wouldn't work very well because they're all different. So a closed loop eliminates the sensitivity to that exact system being controlled. And then more stable is because we actually have some kind of feedback coming in. So our diagrams now can get a little bit more complicated because we're going to start adding in summing points, which are going to look sort of like, and you can think of them sort of like operational amplifiers, because in an analog system, that's how we implement them. Okay, so the symbol that you're going to see is a circle with an X in it, and we call that a summing point. What we're going to do is in each quadrant of this, you put the operator that you're going to use, so a plus or a minus. So for example, if I had a summing point, I had plus and plus, I have A coming in here, B coming in here, and the output is A plus B, right? It's relatively straightforward. Even though it's called a summing point, we can replace that with a minus and get a minus B coming, all right? So you can do this for any number of operations. So just everything coming in happens, right? So addition and subtraction are, you can put them in any order you want, they're communicative. So you just, everything that's not the output gets added or subtracted.
So the output is always on the right side?
Generally, yeah.
I don't know how complicated these figures you get, but an interesting thing about the dryer case or the automobile or the thermostat is that the dryer has only got a one side of the system. If you say you want a certain humidity and it gets below that humidity, then it just turns off. It doesn't have a way to add water. So I really do want this humidity, so I'm going to add water. And a lot of heating systems, yeah, you either get heat or you have to choose heat or cold, right? It's very rare to find a system that says it's going to cool down as soon as it gets too hot in the wintertime. Right? You just don't worry about it. But in a lot of systems, that's not good enough, right? Serial control system like we run upstairs.
Right.
That would be like, okay, I've gotten there, now I went too far, and I don't really care that I went too far, and I'll just wait until something happens. Right?
Yeah, exactly. So it's like a push-pull system versus just a push system.
There are plenty of examples where you only have one side of that.
Yeah, and I guess the
car doesn't put the brakes on.
yeah,
Fortunately,
exactly.
Inertia, gravity, various other things kind of wait to get going too fast and just go slow down.
I guess unless it's maybe like if you had a Tesla Model S that was driving itself, right? Then it can do the whole thing. Yeah. So we're going to draw a generalized closed loop representation of the closed loop. And we're going to use a little bit more formal notation now. So theta I is the input. It's going to go in to a summing point. It's going to have plus and minus. Then we've got the error signal. That's going into your plant or your process or whatever. We're going to call that G. And in reality, it's probably something like G is a function of frequency and something else and something else. And there's a bunch of variables that are tacked on to there that it's a function of. And then you're going to get the output. Got a node here that comes down, goes back to some sensing process. We're going to call H of whatever. And that's going to come in to the summing point, right? So a little bit more formal way to draw the closed loop. The top part of this diagram, so from here this way, is called the forward path, which is all that you've got in an open loop system. And any arrows pointing this way are the feedback path. Okay. Everybody feel comfortable with a single variable that we're controlling and a single way to control it? Because it just gets worse. Okay. So, you can have a system that has multiple control loops operating together. And they can be in a bunch of different configurations. So multi-loop system, each manipulated variable depends on only a single controlled variable. So, for example, furnace fuel air to control a flame or something like that. Diagram for that, right, it's going to be a little bit more complicated than this one. We're going to have our input, theta I. Going to go into our summing node. And you can have, of course, multiple processes that output affects, right? So we could have process G1 and process G2, no worries. Got another summing point. And then we've got process G3, process G4, and we finally get to theta O, our output. Can everybody see when I write that far over? Okay. So now here from the output, I'm going to go down. We have some sensor, some sensing process H1 that feeds back to there. And we also have some sensor H2 that feeds back to there, right? So we've got two control loops in series that are controlling the output. Okay, so does that mostly make sense to people? You can see where you could use something like this in a complex system, that you've got multiple things. You have forward pressure and back pressure. You have two different things that you can manipulate to control that output. Okay. So what would the other scenario be that you could imagine from that? So there, the variables, the manipulated variable only is related to a single controlled variable, right? Well, you can have multivariable control. Where each Each manipulated variable can depend on two or more controlled variables. Okay, so what could this look like? You've got all kinds of feedbacks that are going on. So let's say we have theta I1, our first input. It goes into a summing node, goes to our controller. Okay, and then we're going to have, let's put it down here, try to make everything fit. Theta I2 goes to a summing node, goes to its controller. All right. We're going to put a box here. That is the process. We're going to fill it in just a second. So the controllers control something, goes into the process. The output of the process, we have theta out 1, theta out 2. There's going to be some kind of feedback path. Let's see, I'll just label it sensor here. Move our minus sign up there, make it a little bit easier to draw. There's going to be a feedback path down here through a sensor. But what's going on inside the process? Because these variables can all talk to each other. This is where it gets ugly when you're modeling it, right? So we're actually going to have 4 nodes in here. We've got the process going into there and into there. This process goes into there and into there. Let me write this up here real quick, and then we're going to go over it and give people a chance to catch up writing a little. Summing node goes there. Okay, so you've got the first variable. The first variable has some effect on the thing it's trying to control, right? Makes sense. Something on output 1. It's also going to have some effect on the second variable that we're trying to control, because these two systems are linked. So second variable, the effect of the first variable, the effect of the first. The second variable that we're trying to control, it's going to have some effect on itself, hopefully. We've designed our system. And it's going to have some effect on the first variable, because these things crosstalk with each other. And then the output of the effect of, so let's look at the first one. The effect of the first variable on the first output and the effect of the second variable on the first output get mixed together to create the actual real output. So think about this if you're trying to control combustion in the engine in your car. You're controlling the amount of fuel that's going in, and you're separately controlling the amount of air that's going in. These two things are interrelated. If you add more fuel, you need to add more air, right? Otherwise, the engine's going to run too rich or run too lean. So those two processes cross-communicate with each other, and your control loop gets a lot more complicated. This is just two variables interacting with each other. In something like a distillation column in an oil refinery, where you're controlling temperature, you have a chemical reaction going on, you have multiple things precipitating out of the column. These things can literally take like a table of control diagrams for modeling how the process works. And it's not going to be a perfect model, right? So does this whole process of mixing all these signals together make sense? If you look at radio diagrams, how like your AM or FM radio works, you'll see this exact symbol in there a lot. And it's for a mixer electrically. So sometimes you'll hear people in control diagrams refer to these as mixers as well. Okay. Good? All right. I'm going to show you a really simple circuit that actually probably should have tried to build, but didn't have the time to before class, to control the speed of a DC motor. So let's say that you've got a motor that is spinning a pump or spinning some process that you need to control its speed. So we're going to represent the motor with a circle with an M in it. That's pretty standard. And this is going to be a closed loop system. So how do you detect the speed of some? What's an instrument called that measures the speed of rotation of something? You would hook it up to like your car and it had a flashing light, a timing light, but it's pretty similar. Tachometer, right? So that other gauge that nobody ever looks at on your dash that's to the left of the speed, that's the speed of your engine, it's the tachometer. All right, so we're going to represent that with a circle and a T. We're going to have everybody's favorite, the voltage divider. We're going to feed that into an op-amp. Op-amp output is going to go into our motor. These need a ground so that they operate properly. And the tachometer is going to be in the feedback loop for our system, right? So we're measuring the speed, and the difference between this voltage that we've set and the voltage that's coming out of our tachometer is going to drive the op-amp to speed up or slow down the motor. So you would hear, or you would see things labeled. This often is labeled SP, which is the set point. It's where we want it to be. And the thing that we're controlling, which is speed in this case, you often see notated as PV, or process variable. Okay, so do people see how that could feasibly work? See that this is one of these summing points, just like we said. Okay, so there are several ways that you could implement control systems in the real world. All these are kind of theoretical diagrams, and we're not, other than that, we haven't talked about an actual way to implement it. The way that used to be what all the cool kids did, so these things called PLD, programmable logic devices, or something like that. Used to be used to control things like conveyors and plants and that kind of thing. They're getting a little bit long in the tooth now, but you still find them around. So the first way that you can do it is with a system called logic control. Okay, so it was implemented with relays in the old days. This would be like probably the system that controlled our elevators until they were redone, very likely. You create logic gates with relays, and we talked about before and, or, NAND, NOR, all of those kind of gates. So you can imagine that the logic control for an elevator might be something like, are the doors open? Is there something obstructing the door? If either or of those is true, then don't move, that kind of thing. So you can see how a logic control system could be built up that way. So they're now implemented with microcontrollers like your Arduino, because you can program logic operations, as we've seen, or PLCs, programmable logic controllers. And so these just use a series of binary inputs, so ons or offs, to determine the action to take. So did somebody push the elevator call button on the 3rd floor? Are there people that are going somewhere in the elevator currently? All of these things would be part of the logic control system. And that was all designed with something called ladder logic. It was from when there were racks of relays. You would make these ladder diagrams. Some of the PLC manufacturers still use ladder logic as a paradigm. So you're creating this virtual logic circuit, kind of in a GUI LabVIEW looking thing, to program your PLC. So it's not a dead notation. It's just old, but still used. So an example, let's just try to put them down here. So we got elevators. Anybody think of another ladder logic controlled device? Probably. The washing machine, most likely. You know, is the door open? Then stop, that kind of thing. And then simple industrial controllers, conveyor belt controllers, that kind of thing. All right. Another way that you can control systems, and this would be maybe how the thermostat would work, is with on-off control. So we have no proportional control over how things work. Your refrigerator would be a good example of this. Okay, so the system has 2 states. On and off. You'll also hear this referred to as bang-bang control, because you're all the way on, you're all the way off. If you turn your heat, if you get home and it's really cold and you turn your heater up to 80, it doesn't warm your house any faster than if you set it to 72 like a sane person, right? Because the heater is all the way on or it's all the way off. So thermostats are a good example. Let's see, so refrigerators, freezers, air compressors. You know, if you air up the tire in your car and the pressure in the tank falls below a certain threshold, the air compressor kicks on, and it's on until the tank is filled up to some threshold, right? It's an on-off controller. So a disadvantage of these guys is they can switch rapidly if the system is evolving a lot, which is hard on equipment and possibly expensive if your equipment has a very large electrical current to start up and shut down all the time, for example. So generally, hysteresis is added. Hysteresis is added to produce a dead band. Which is just the engineering term for a section of the state space of the system where the system is not sensitive. It does not respond. It is dead. So let's look at a freezer. A freezer is a really good example of an on-off controller that has a dead band. So we're going to make a graph of time and temperature. And we need 2 colors to do this effectively here. So we're going to say that this dashed line is the set point. That is where the USDA recommends, or Food and Safety, whatever administration recommends that you have your freezer set to. If we have no hysteresis, then we're going to get these rapid on-off cycles, right? So what's going to happen when we turn this controller on is we're going to very quickly have a boat anchor that doesn't work. Because we start out, we cool down, we hit the set point. We're there. Shut off the freezer compressor. We're done. We start to warm back up. Oh, we're not at the set point anymore. Turn the compressor back on. Okay, we're at the set point. Turn it off. Turn it back on. And it just oscillates right around that set point, turning the freezer off and on all the time until your compressor burns out and you're sad. If we add a little bit of hysteresis to this, we're going to make the same plot roughly on the same scale here. Time, temperature. We put our set point. And now we're going to add a deadband. This is going to be just like adding hysteresis to the op amps that we talked about a couple weeks ago. So we're going to start out up here, we're going to cool down. This is our set point right now. We're set here, but because of the hysteresis, we're aiming for below. So we hit there and we say, okay, fine, we're good. We shut the freezer off. The set point now changes to above the actual set point. So we warm up, and we have some kind of nice Newton warming cooling curve, right? And then we hit that, we turn back on, we cool down. We warm up, we cool down. We warm up, we cool down. We do this over and over, and we get much fewer on-off cycles for that given design. So in that case, we would say that it has hysteresis, and it has a reduced duty cycle. Meaning that it's switching on and off less. And it has a pretty small temperature error in this case. I mean, let's say that we even set this to be plus or minus 1 or 2 degrees, right? That's not going to change the health and safety of your food much, and it's going to make your compressor last a lot longer. There's one more possibility in this case. Let's call that little t and big T. So I don't have to write down there. And then we have our set point. And we're going to set a much wider band for our hysteresis now. So we have a much bigger dead band in the system. Now what this looks like is we cool down, warm up, cool down, warm up, cool down, warm up, start to cool down again. So in this case, we have a larger dead band. And we have a low duty cycle. And we have large temperature error. So if your system can tolerate these kind of large errors, this is a good thing to do because it results in fewer on-off cycles of your equipment. It's better on the equipment. It's an easier control system to implement, right? So make the dead band as big as you can stand it for a given system if it's an on-off or bang-bang type system. So what if we had a system, let's say we had a heater in our house, that we could control how much power we were applying to it within some limits? Kind of like a dimmer switch on a heater, let's say. Can you think of a way that we could control that? That's not just on-off. So we've got an error signal. We know we want to be here and we're here, so we have a magnitude of an error, and we can turn this knob for the heater varying amounts. So what kind of relation could we use there, maybe? So we could implement, it's called a proportional control. So the control signal that's going out to our plant or process is produced with linear, and we'll just say linear feedback. So the output could be or may be a directly variable signal or a pulse width modulation, PWM, duty cycle control. So what that means is if I am dimming the spotlights, which are halogen, all that I'm doing is changing the voltage that's going to them. I can set the voltage anywhere between, let's say, 0 and 120 volts AC. Anything in between is fair game. LED lights and fluorescent lights, you can't do that. They don't really work that way very well. So we do that duty cycle control. We change the on and off time very rapidly with pulse width modulation, like we talked about in one of the early lectures. So you can do it either way, really. But you're just going for a proportional control. The bigger the air, the harder you're going to try to fix the air. And then as the air gets reduced and reduced and reduced, you start backing off on the air correction signal. That leads to a problem, though, of without proper damping, these systems oscillate. So what happens is you're coming up, here's your set point, you're coming up, okay, we're going to start backing off. Oh, we overshot, now we're going to go back down. Oh, we undershot, now we're going to, and you just kind of oscillate around that set point continuously. There is a way to get around that. You can add some damping to your system. A lot of what we would say non-stiff systems have damping mechanically in them. You know, if you're mixing things in a tank, you've got a little bit of a buffer there physically. Or if you're controlling a hydraulic ram, you have the compliance of the ram and the system and the fluid and all of that that's helping damp that oscillation. But if you have a system that's sufficiently stiff so that it's hard to control, you need to do a little bit more. This is a topic of an entire course, multiple courses really in engineering, on control system dynamics. I think everybody's probably seen the friction phase space plots. Well, a phase space plot's just a way to plot a system of differential equations. You can do the same thing for control systems. And you can create plots of whether the control system is going to be stable or unstable or when it's going to be unstable. We're not going to do that, don't worry. But we are going to talk about kind of the crux of what we've been building up to this whole time, which is PID control. This is how most, I would say probably most closed-loop control systems in production are implemented. This is how your cruise control works. This is how pretty much any proportional type control system works nowadays. So, PID control takes into account the past, present, and future state of the system to determine the output. So it's kind of this magic time machine, right? We can look into the past pretty easily, but we can also see into the future, and you'll see how that's done in just a second. Okay, so we're going to make a diagram for a PID system. First, we have our process. Okay, and it's going to have some input. I'm not going to draw any more than that right now. And it's going to have its output. You can call that Y of t if you want to be consistent with how you'll see it diagrammed in most texts. Have our summing point, or summing node. Have the set point where we want to be, and the output where we actually are. So this is producing an error signal. I want to call that E of t. And that is actually going to feed back into 3 boxes. Can anybody guess what the 3 boxes are? Yeah, so P, I, and D. We're creative with the naming of this thing, right? So P is proportional. It's what we just talked about. The further we are from where we want to be, we're going to crank it up. And it's going to have some gain. These gains in control systems are generally written as a K, capital K. So K sub P times the error signal. Some multiplier times how far we are from where we want to be. The I term is, so that's the present state of the system, right? Where we are now, where we want to be. The I term is an integral. So there's a gain, K sub I, an integral. Let's be mathematically proper. So we're going to 0 to t of E sub tau d tau. So this is the past. This is accumulated error, and we'll talk about why we need that in just a second. And then D, we got K sub D, dE of t, dt. So the derivative of the error signal. So this is the future. This is projecting, based on the rate of change of the error signal that we have up till now, what is the error signal going to be the next time I run through this loop, right? These all feed into, let's see, a summing node. So here's a case where we've got 3 points in our summing node, and that feeds back into the process. So this entire thing is the PID loop. And generally, you need to go through this pretty darn fast, depending on what you're trying to control. 100 hertz is a kind of low-end number for how fast you should be running through this loop. When we did some propulsion control and that kind of thing, I think our PID loops were running at 600 or 800 hertz. So this needs to be pretty compact. Okay, proportional. I'm going to go through all the parts here real quick. So the output is directly scaled with the magnitude of the error signal. So this is the present term in our past, present, future. This will kick a system with mass or inertia into oscillations. Okay, so a good example of this, there's not really anything on a string here that'll work. If you can imagine, I've got something, I have a ball on the end of a string, right? As I deviate that from hanging straight down, the force exerted on that ball is going up, right? Then we let go. In this case, it just swung and stopped because I have all kinds of resistance on this. Ideally, the pendulum would keep oscillating. It would overshoot, and then we would start trying to correct this way, and we'd start trying to correct this way. That's what I mean by mass or inertia. This could be thermal inertia, this could be physical mass, it could be anything in a real system that you're trying to control. Okay, the integral term. So this is sum of error over time. It's the past term. And it keeps small errors from persisting. Due to small error signal. And it's generally too slow to be used alone. So you don't ever see just an I controller. You know, we see just P controllers, but you never see just I. So what this means is if you're just having a proportional signal coming into your process, as your error gets very small, the correction signal gets very, very small, right? And in a real system with mass and inertia, when the error or when the correction signal gets very small, the system just eventually doesn't respond. So you get very close to your set point. Let's say we wanted, I'll show you a video of this in a little bit. Say we wanted, our thing to stand or hang straight down. Well, you might get close and then we're close enough. So this over time, that integral, the error builds up and builds up. This term gets larger and larger until the process finally gets to where it's supposed to be. You'll see this in a lab that we're going to do next time after the break. You're going to build a little PID controller. And differential. So this is the time-traveling one that predicts the future of the system. It helps prevent overshoot of the control system. And excess results in jittery control. Right, so you know that derivatives can be noisy, especially of real data. So if you have too much derivative gain, K sub d, the system will just continually sit there and jitter. What it is good at, though, is if it knows that your error signal is changing at 3 degrees per hour, let's say, in some kind of system, it's going to know to start pulling back before you hit your set point. So you don't overshoot that set point. All right, so any questions on a PID controller? All right, so I'm going to show you now, maybe. Oh, let me put the screen down. So this person has built, and I would like to have had time to build to show you physically, but didn't, a servo, basically, which means that it's a DC motor. It's got some kind of position sensor on it, a position encoder, and they say go to this position, and the motor tries to get there, much like the servos in your inventor's kits. There's no audio. They have some subtitles, but I'll kind of narrate for you a little bit. All these designs are online if somebody wants to build it. That's kind of a neat thing. And the spinning wheel of death from the Mac, because no technology wants to work in this room.
What internet are you on?
Should be on PSU. Yeah, I'm on PSU.
Is it linked on the Forceful site yet?
It's not yet. So we're going to quit Safari and try it again. So is anybody going to have a PID controller in their project? I know there's somebody that's doing a pump, right, I think, or a pressure-controlled pump. Yeah, so you'll probably have a PID, or at least P controller in your system. Okay, I think we're playing, yes. Okay, maybe. Okay, well now it's playing and it won't project. Try it again. You have to be kidding me.
Wow.
Can we try your laptop, Chris?
Yeah, happy
I can find it on YouTube pretty quickly.
Oh, it's on YouTube, okay, yeah.
Um,
Mine's on that side.
oh, okay.
Here, I'll play with it.
PID demo.
Yeah, it's starting to talk.
Okay. We're going to try it again.
It's going.
All right. So the power is off. You see, you can just put the motor anywhere you want it. It's going to stay. So this is just Pid Control with a P gain of 200. Ideally, it should be going to the center. You see, it gets close, but then the air signal's so small, it never gets all the way to where it's going. So he ups the P gain. It's better, but it still has that offset air. And it does this overshooting, annoying behavior, which you really don't want in most systems. Okay, so now added a KD of 25, and hey, that's pretty good, right? It came up to where it's supposed to be, or close to where it's supposed to be and stopped, but there's still the steady state offsets, because there's no I gain. So now it's just a PI system, took the derivative term out. So there's overshoot, but look, the integral over time pulls it exactly where it's supposed to be. You can see it takes a little bit longer to do it though, right? Because you have to let that error accumulate over time. It's this time sum. So now, this is the one thing that we didn't talk about, which is you have to add something called wind-up to a lot of physical systems. So it basically just turns off the integral when you're already at the maximum output. When you're applying the max power to the motor in this case, it just turns off the integral term. So that looks pretty good. But if you turn the P gain way up, it oscillates. So if you turn the rate up, it's better. There's still some oscillation in there. Now we're going really fast, 800 hertz. And bang, it goes right to where it's supposed to be and stops, right? Okay. There was a recent discussion about some of this on this forum that I spend a decent amount of time on. This is a really cool PID demo. So we have two reaction wheels. These are just flywheels that are attached to motors, right? And so we know they have this whole inertia thing going on. Stand it up, activate the PID system, and that stick can stand on a point just by using the PID control to rotate those two wheels. This is how like self-balancing robots, segways, all that stuff stay upright. They have PID loops. So that's a pretty neat thing to be able to do with a pretty minimal amount of math. And they go on to show you, so the set point is in blue and the current position is in green. Now they can add some mass to the system, which in a simple controller would have already toppled it over, and it can accommodate it. There are ways that you can auto-tune PID controllers that people have come up with. I'm not going to have time to talk about any of those because we're out of time in 3 minutes here. The inverted pendulum is a common PID demo. This is another one where you have a ball on this plate and a vision system above it that's tracking the position of the ball. And so you can keep the ball in a fixed position on the plate using these PID systems. I think if we go on, yeah, so now he's got a Wii nunchuck controller that you can control where on the platform you want the ball to be sitting. I've seen people do like maze games with these kind of things. So this is another reaction wheel based PID systems. There are 3 reaction wheels in here that are keeping this cube balanced on its edge. It can do all kinds of fun things. It can also stand itself up, so it can there. So build up a lot of inertia in the wheel and then flip itself up on its edge and maintain balance there. So you can control really finicky systems with PID controllers. And there's this video that I'll also link in. It's this guy, if you like Australians, this guy's got a great Australian accent. And his explanation I thought was very, very clear. So any questions on control systems, PID, on-off, anything like that? It's a lot of stuff, but if you're doing anything in the lab, you're controlling some variables, so you have to have a control system of some kind. No? Okay, so over break, projects, right? Because we have 1 week of class after break, and then project presentations. We're going to try to get the project presentation guidelines on the website, hopefully later today. Other than that, after break, how many of you have your project built on your breadboard with your Arduino kit and would feel absolutely horrible if you had to tear it all off to do an activity on Tuesday? 3 people? 4 people? Okay. So I'll try to bring some extra breadboards. Bring your kit on Tuesday when we get back from break, because you're going to build a PID system where you have an LED looking at a photocell, so a light sensor, and you're going to make a dimmer, much like the dimmers in this room, that would be sensitive to the amount of light in the room. So you can set the LED brightness, you set the amount of light you want falling on that surface, and it will hold it constant, whether we brighten the room lights, dim the room lights, whatever, much like your laptop does. When you go out in the sun, it brightens the screen, that kind of thing.